Good morning students, welcome to the online video class of Sri Kogulam Public School, Guruvayur. I hope all of you are safe and fine.
In previous class, we had discussed about electrical properties of solids. Based on the conductivity, the solids are classified as, what are they? Insulators, conductors and semiconductors. There we have learnt metals are the good conductors of electricity. And what is the reason for metals are the good conductors of electricity? Why the metal conduct electricity and insulators do not conduct electricity? In this section, you will learn about electrical conductivity of conductors, insulators and semiconductors. Conduction of electricity in metals. A conductor may conduct electricity through movement of electrons or ions. If the conductivity is due to the movement of electrons, it is metallic conductivity. And if the conductivity is due to the movement of ions, it is electrolytic conductivity. Metals conduct electricity in solid as well as molten state. The conductivity of metal depends upon the number of valence electrons available per atom. So the conductivity depends upon the number of valence electrons in an atom. The atomic orbitals of metal atom form molecular orbitals, which are so close in energy to each other as to form a band. You have learned in class 11 that in the combination of one atomic orbital belonging to two atom, two molecular orbitals are formed. How the molecular orbitals are formed? By the combination of atomic orbitals. Next, we are going to study about how the variation of electrical conductivity can be explained with the help of band theory. How the electrical conductance are occurred between valence band and conduction band? Under the influence of applied current, the electrons from the valence band easily shift towards the conduction band, which is empty or vacant band, thus leading to electrical conductance. And the band which holds electrons are valence band, and the band which is vacant and is responsible for the electrical conductance due to the electron shift is called conduction band. Let's look how the electrical conductance occurs in the case of magnesium. Atomic number of magnesium, it is 12, and its subshell electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p0. Then the electrical conductance here occurs between 3s and 3p orbitals. 3s and 3p. Here 3s orbital contain valence electrons and 3p orbital is vacant. The electron shift occurs from 3s band to 3p band. Therefore, the electrical conductance of magnesium is due to the electron shift from 3s orbital, that is valence band, to 3p orbital, conduction band, which is empty. In the case of conductors, the gap between partially filled valence band and unoccupied conduction band is negligible. Rather, it gets overlap and electrons flow easily under the influence of an applied electric field. And the metal show conductivity. In the case of semiconductors, there is a small gap between the partially filled valence band and conduction band. So some of the electrons from the valence band jump into the conduction band and show some conductivity. The conductivity of semiconductors increases with increasing temperature. In the case of insulator, the gap between valence band and occupied conduction band is very large. So the electrons cannot jump into the conduction band. Here the conductivity is very small. Therefore, it behaves like insulators. Next topic is conduction of electric current in semiconductors. We have studied that pure silicon and pure germanium are poor conductors of electricity and are regarded as insulators. However, their conductivity can be increased by increasing temperature and by adding the impurities of suitable metals or by doping. By increasing temperature. Upon increasing the temperature, some electrons are in a position to move from valence band to the conduction band, and the electric conductance thus increases. Such type of semiconductor form as a result of increasing temperature are known as intrinsic semiconductors. This picture shows the crystalline structure of intrinsic semiconductor. And as I told you, silicon is a poor conductor of electricity, silicon and germanium, and its conductivity can be increased by increasing its temperature. Here, the silicon is covalently bonded with the 4 other silicon atoms. The valency of silicon is 4. In order to attain stability, it needs 4 more electrons to complete its octet. So here the silicon is covalently bonded with the 4 other silicon atoms. As the temperature increases, it acquires some thermal energy. Due to this, the bond breaks. The covalent bond breaks and electrons are free to move. Then electrons move from valence band to conduction band. Electrical conductance occurs. Can also increase the conductivity by adding the impurities of suitable metals or by doping. The conductivity of intrinsic semiconductors is still very low and has hardly any utility. This can be further increased by adding small amount of either electron-rich element belonging to higher group or electron-deficient element belonging to lower group. This acts as impurities and this process is called doping. Thus, doping may be defined as the process of increasing the conductivity of insulators by the addition of certain impurities. The semiconductors formed as a result of doping are known as eccentric semiconductors. Let us study doping in details. Impurity or N-type semiconductor. When any pentavalent element such as phosphorus, arsenic or antimony, which involves in the 15th group of the periodic table, is added to intrinsic semiconductor, 4 electrons are involved in covalent bonding with the 4 neighboring pure semiconductors. Intrinsic semiconductor involves silicon or germanium. The fifth electron is weakly bonded to the parent atom, and even for lesser thermal energy, it is released, leaving the parent atom positively ionized. Let us study N-type semiconductor more details. Electron-rich impurity can be added by doping with the elements like phosphorus, arsenic, antimony of group 15 having 5 valence electrons. Their atoms occupy some of the lattice site of silicon or germanium. Here the phosphorus is taken as example. How many electrons are there in outermost shell of phosphorus? 5. Its valency is 5. Out of 5 electrons, 4 are covalently bonded with the silicon atoms. And the 5th electron are not involved in bonding, is extra as well as delocalized. And these delocalized electrons are responsible for increase in the electrical conductivity of doped silicon or germanium. The doped element is called N-type semiconductor because the electrical conductivity increases due to negative charge electron. Next is electron defect impurity or electron deficient impurity. It is also called P-type semiconductor. Silicon or germanium can be doped with the group 13 elements like boron, aluminum or gallium, which contain only 3 valence electrons. The place where the 4th electron is missing is called electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole, but in doing so it would leave an electron hole as its original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of electron that filled it. Under the influence of electric field, electron would move towards the positively charged plate through electronic holes, but it would appear as if electron holes are positively charged and are moving towards negatively charged plates. This type of semiconductor are called P-type semiconductor. In the case of P-type semiconductor, the group 13 elements have only 3 valence electrons. They combine with the silicon or germanium to form 3 covalent bonds, and an electron deficient bond or hole is produced there. This hole can move across the crystal, giving rise to positive hole conduction. And silicon and germanium doped with the group 13 or group 15 act as semiconductors. Let us explain what is P-type eccentric semiconductor using an example. The doping of elements of group 14 can be achieved by adding elements of group 13. Here we take boron and silicon as examples. Boron belongs to 13th group of the periodic table and its outermost shell contains 3 valence electrons. And silicon is 14th group element in the periodic table and its outermost shell contains 4 valence electrons. And the electrons in boron atom shared by 3 electrons of atoms of elements belonging to silicon atom. Since the 4th electron is missing, an electron vacancy of electron hole is created in the crystal lattice of group 14 atom as shown in this figure. Electron from a neighboring atom can come and fill this hole. However, in doing so, another hole is created. Thus, it appears as if the electron hole has moved in the direction opposite to that of electron that filled it. When electric field is applied, the electrons tend to move towards the positively charged plate through electronic hole. Since holes move in oppositely charged direction, they tend to move towards negatively charged plate and thus appear to carry positive charge. However, these are neutral nature. Consequently, the electrical conductivity of semiconductor increases because of electron deficient impurity. The doped element is called p-type semiconductor, where P stands for positive sign. What is the difference between intrinsic semiconductor and eccentric semiconductor? Intrinsic semiconductor are pure semiconductor and no impurities are added to it. Eccentric semiconductors is prepared by doping a small quantity of impurity atom to the pure semiconductor material. And the extrinsic semiconductors are two types, N-type and P-type semiconductors. The number of free electrons and holes is never equal. There is excess of electrons in N-type semiconductor and excess of holes in P-type semiconductors. Its electrical conductivity is high. In the case of intrinsic semiconductor, electric conductivity is low. Applications of N-type and P-type semiconductors. Some important applications of P-type and N-type semiconductors are: it is used as rectifier. Diode is a combination of N-type and P-type semiconductor and is used as rectifier. And transistors are made by sandwiching a layer of one type of semiconductor between two layers of other type of semiconductors. NPN and PNP type of transistors are used to detect or amplify radio or audio signals. The solar cell is an efficient photodiode used for conversion of light energy into electrical energy. In this section, we have discussed about electrical properties of solids and also about semiconductors. There are two types of semiconductors, N-type and P-type. I hope all of you understand what we learned today.